Okay, so this is a basic problem in terms of our design of our reactors. So all these are, of course, isothermal reactor design. I know it's in the title, but we didn't really comment on that. So isothermal, it means we are assuming the temperature is the same everywhere. So whatever the reactor type is, right, whether it's a CSTR or a PFR or a batch reactor, whatever it is, we are assuming that the temperature is the same everywhere, right, for now. We will be relaxing that very soon. In fact, in the next section, we'll be relaxing that. We will allow temperature variations after this section. But for right now, we are assuming that if we look at the temperature here, then that's the same as the temperature here, and it's the same as the temperature here. So at any point in the system, the temperature is the same. And it's important to say that because that means the reaction rate is the same, at least with respect to temperature. Of course, in the case of the PFR and any reactor where there's a concentration gradient, then the reaction rate can change because of concentration changes. But in terms of temperature, temperature is not affecting the rate, at least for now. Okay, so isothermal reactor design, and then there's our Levenspiel plot. And you see, this plot would be more complicated if we were taking temperature into account, because as your conversion rises, your temperature will change, and that's going to change your reaction rate. So, for example, if you have a highly exothermic reaction, then as you convert more of your reactant, your temperature will rise, and so your reaction rate will rise. So bear that in mind. That's the kind of complication we'll be dealing with in the next section. For now, we are assuming it's the same temperature everywhere, and that's how we develop everything in this course. We start out with a very simple set of, well, an extreme set of simplifying assumptions. We assume the most simple reactor, you know, it's perfectly mixed, or it's perfectly not mixed, or it's isothermal. And then in each section, we relax that, and we get closer and closer to real world reactors. So anyway, in this problem, we are told it's first order, and there's the rate constant. Actually, I don't think we need it. I'm not sure we need it, because when you get a Levenspiel plot, that actually tells you everything you need to know about the reactor. So we'll see, maybe we'll see if we need this data later. Anyway, the intention is we want to convert 50% of the reactant, which is available at 20,000 moles per cubic meter. And the flow rate is given also. So that's our FA naught. And there's our Levenspiel plot. And we want to know the volume of each of the reactor types and the space times and so on. So let's quickly then just look at what those are. So, so in terms of the CSTR, if you follow the derivations we've done before, so for the CSTR, we have the volume being, the volume is, so it's minus FA naught X equals R A V. And let's see if we can just answer what's the volume for the CSTR. So by the way, always go back, just revise and see you can derive this thing quickly. And let's see if we can work out the volume quickly from this equation. So it's simply V equals, and it's just this side divided by RA. Right, so that's what we need to evaluate. So FA naught is given to us, and X is also, and RA we can read off. So let's do it. So FA naught, the molar flow of component A, is 400. So that's 400 moles per second, and then the mole fraction, the conversion that we want to achieve is 50%. So we want to convert 50% of that stream. So we just say here 0.5 times 0.5, and then we need the reaction rate. So here, of course, we are given -1/RA, and we know we want to achieve 50%. So it's a simple matter of reading this off. So at 50%, we can see it's around about 0.2. And this is written as -1/RA. So we can say this is times 0.2. And it's a -RA, so we can let those two cancel. So that's the volume that we need. So the first one, the volume of the CSTR, is calculated as simply as this. So this is what, 0.1, so this is 40 cubic meters, right? And that's a typical reactor volume. I must say, I do spend some time just checking that my numbers in my problems are fairly reasonable. So a 50 cubic meter reactor or a 40 cubic meter reactor, that's fairly standard. So so the numbers look good. So on my courses, you shouldn't find dust-sized reactors or kilometers tall towers and things like that, right? So that's the CSTR so far. Then for the PFR, of course, we have, so let's just note that. So for the PFR, we have FA naught dx dV equals RA minus RA. And always just stop and check the units quickly. So this is moles per second divided by volume. So that's moles per cubic meter per second. Of course, conversion has no units, so moles per cubic meter per second. And RA, we know the standard units, moles per cubic meter per second. So that equation looks fine. And you can also check by looking up here that the X's and the V's are in the right position. So if you divide by V here, you'll get FA naught X over V, which is similar enough to this one here. Okay, so again, always rederive your equation, check it's correct. So that's what we have. So that's what we have, but what we want now is the volume. So we need to integrate this expression towards getting the volume. So we can write this as, let's see, so it's going to be FA naught, and it's going to be the integral of 1/RA or -1/RA in dx. So we are integrating in dx, and it's in -RA, -1/RA. That's not quite right. Let's see. Okay, so it's more like this. So that's what we want, right? So that's what we are trying to integrate here. And of course, FA naught is known, and now we need this integral. And if you look at the plot that we have, we've got -1/RA here, which is this line. And so if we want to integrate -1/RA, then we are simply talking about the area under the curve. And let's do this a little bit separately. Let's just snip this. And let's talk about doing the integration. And when you do these integrations, you want to make it easy on yourself, right? So just quickly, what we want to do is integrate from here, right, 0.5. So we want this area. So we know we want to achieve a conversion of 0.5. So the PFR must be long enough to reach 0.5 by the exit. And so we want this area. We want the area underneath this curve here. And, you know, I know everybody knows Simpson's rule, and it seems like the obvious thing, just start with that formula. But if you look at this, the area here is really a very simple thing to work out. If you look at it, you can draw a line like this, and you can see that's a good enough approximation of the area that we need. So this area, we can say, well, it's simply going to be 0.5 times the average of these two heights, which is about 0.2 and 0.1, right? So, so we can say here, around the plot, drawing a simple straight line, we can see that the area, which is given by the integral of, let's see, so it's dx, and we are integrating -1 over r a here, right? So we can see that that area can be obtained simply as maybe let's explain what we are doing here, but so we can say delta x, by this I mean delta x equals 0.5 and a mean -1 over r a of, and we're going to say 1/2, and it's 0.1 plus 0.2, so that's 0.15, right? So the mean height in this region is 0.15, and then the width here is 0.5. So our required volume is, and then for this, we know it is, FA naught was, what was that, 400, the molar flow of A. And then this area we've said is simply delta X. So we say here times 0.5 and then times 0.15. Yeah. Okay, so this is 200. This part is 200, and then 1/10 of 200 is 20, and half of that is 10. So that's a 30. So that's 30 cubic meters. Okay. So always take a, yeah, I just want to belabor this point a bit. I do see people taking, sometimes you'll take 6 points and you'll perform Simpson's rule on each one. You're not going to get any marks for doing that, right? I know we can, in fact, I should credit someone for taking a simpler route and acknowledging that, okay, this is such a shallow curve. This is going to be a very good approximation to that curve. You can also see my chosen value here of 0.2 is not great, right? 0.2 is more here. But in terms of this kind of problem, it's fine. Just take 0.2, the numbers, you can do this whole thing mentally. So this is fine. You would get full marks for even some slight approximations I used over here. Of course, if we were doing this for the purpose of actually designing a reactor, then I would go and actually integrate under this curve, or better, it says it's a first order reaction. So I would actually derive this analytically and get the precise volume. But of course, in a problem like this, where we are testing the method more than anything, and we do want to get reasonable numbers, close numbers, yeah, we don't want to go to extremes, right? So just strike that balance so that you can do these problems quickly. Any questions or comments there? And by the way, maybe just again to to talk about this point further. If you do have a slightly more complicated curve, so let's say you've got a curve like this, then the way to choose your points better, just take regions where you can see approximately straight lines, right? So I would, if I wanted the area under this curve, then I would probably take a line here and then another line like that and so on. So you look at where the gradient is changing more and you just approximate the line like that. So you can probably do this integral reasonably with the reasonable accuracy with just, what is that, 5 segments. So with 5 calculations, you can get that. Right. So it's as easy as that. So when you saw these integrals and all of that, you see now it's much more concrete and simple than it looks when you just look at the equation, right? And then, of course, the thing we want to comment on is that we have 40 cubic meters here. So in the CSTR, for us to achieve a 50% conversion, we need 40 cubic meters, whereas in the PFR, to achieve the same conversion, we only need 30 cubic meters. And that's just because, as we said, I think 2 times now, in the CSTR, everything is stuck to one concentration everywhere. So it's flowing, but because the CSTR has such extreme mixing, even if you are feeding pure reactant in, so no conversion in the material that just enters, still everything is instantaneously mixed so that you've got the same concentration everywhere in this reactor. And that means you're stuck to the same low rate everywhere. Whereas in the PFR, near the entry point, you've got a nice high concentration of A. And so your reaction rate, you can enjoy a higher reaction rate over here. And so overall, you get better use of your space, or you can do the same thing in a smaller space. Okay, any questions or comments there? So that's the PFR, and what's the corresponding batch reactor? So for the batch reactor, we have to scratch our heads a little bit because you know, we don't have a time or a we don't have a flow rate. So we need to a little bit translate what's given to us in this problem. And so one thing we can do is say, well, we do seem to want to convert. So our intention, if you look at the original problem, is to convert by 50%, 400 moles per second. Right, so we seem to want to do that. So we could say, well, in 1 second, then I've got 400, I'm starting with 400 moles in my space. So that's one way to say it. Of course, we are not going to try to design a reactor around 1 second. So what we can do is translate this. We can say in 1 hour, for example, in 1 hour, want to convert 50% of 400 times 400 times 3,600. So that's what we want to convert. So that now gives us a time. So if we write our batch balance, we can say the NA DT equals, and then RAV. Right, so if you check the units here, this is moles per second. This is moles per second per cubic meter times cubic meters. This is giving us moles per cubic meter. So it's another design equation. So looking at this, we do have to acknowledge here that XA is a function, NA is a function of X. So the number of moles in the reactor does depend on the current conversion, and the reaction rate also depends on the conversion. Let's think about this. So RA, we do have as a function of conversion graphically, right, from that graph. NA, we can rewrite this as, or let's copy it as NA naught, so it's going to be minus NA naught times X, like that. Okay, so that's one. So we can then interpret this as the time. We can look at the time needed for this. I'm just trying to think of the best way to show this. So yeah, we might as well do it that way. So we can say the volume needed for this to happen. So we're going to take time onto this side. Sorry, time. Yeah, time onto that side. And we're going to take the rates down here. And so we can say here that if we integrate this, then it's going to be, and let's just get rid of these signs here. So this is going to be the integral. And when we integrate this, volume is a time constant, so we'll just call this delta T. Right, and what we said here is we want to convert 400 times 3,600, and so we are saying in 1 hour. So actually it is going to count. So the number of moles here, so let's put the numbers in. So we can say here, we want to convert that number of moles. So we want to convert, that's the number of moles we are going to charge into this reactor. And then we are doing this over the time 3,600 as well. So, so that's what we have there. And then if you look at this, you can cancel 3,600 on both sides. And you can see now that we have the same equation as we had over here, right? So comparing those two, you can see your volume equals 400 times this integral, right? And so 400 times the same integral. So in the batch case, we are going to get the same answer of 30 cubic meters. And we had to do a little bit of translating here because we know we don't have the flow case in our batch reactor, but we looked at the flow and we said, well, a flow like that is equivalent to that in tension. And when you apply that, you see you get the same volume. Okay, any questions or comments there? Right, so this part is pretty straightforward. And I think the reason we are doing this, conceptually, it's not that there's something new here, but of course, we need to be able to solve the problems. And I think what I'm trying to say here is these problems, you might feel they start to look abstract, but when you actually do the examples, you'll see they are very simple. And when you do this, it does grow on you what each of these things mean and how to get the numbers and all of that. So be sure to do these things. Don't just look at them at a high level conceptually and say, okay, it looks fine. Okay, so that was the first one. We've commented, we said the CSTR has the biggest volume. And then we do like CSTRs because we just stick a container and add a stirrer. We stick a stirrer into a container. and that's easy. So we do like to use CSTRs. And so now we are considering using 2 CSTRs in series, and we are halving the conversion responsibilities. So we are now talking about, let's copy a new one. Why is it ghosting? Strange. Let's do that again. I think we need to move that. So let's copy this thing. So now we want to use 2 CSTRs in series. And we know that we are going to stop at 25%. So we are going to, in the first one, we are going to, our volume is going to look like this, right? So of course, if you know the conversion in the first one, then you have to read off the reaction rate. So that is going to be the rate in that first reactor. And so that's the other corner for us. And then, of course, what we actually want is overall 50%. So we take 50%, we locate our rate at 50%, and then that's going to be the second reactor. And it looks like that, right? Okay. And so the areas under here are going to be the volumes of the 2 CSTRs. Should I do this? So I think you can see quite easily here now how to do this calculation. So you've got your delta X 0.25, your height here, maybe this is about 0.17. And then you've got, in this case, it's going to be 0.5 minus 0.25. And then the height here is about 0.2. You do have to be careful with the inlet amount. Yeah, let's be careful with our balance. So our tendency is to say, right, our intuition, which is always a dangerous thing. Our intuition is to say for the second tank, just use the inlet amount. So for the second one, so for the first one, it's straightforward. V1 equals X1, and this is RA1. So the reaction rate at that exit point. So we are using the rate here. So that's your RA1. Now for the second volume, our tendency is to say V2 equals, and we know this needs to be XA2 minus XA1, and we know this is RA. Now that looks automatically this looks fine, but what about this FA naught? So your inlet molar flow rate, that we need to be careful about. So what I would rather do in a case like this is just rederive the equation. And, I will often go all the way to the beginning to say d NA dt equals FA in minus FA out plus integral RA V. And then we know this is, okay, so that's the general one that applies to any possible reactor. And we know we are doing this at steady states. And on the second reactor, so it's a CSTR, so R is a constant. So this is RA2, and this is volume 2. And so now FA in, this is clearly now FA1. So it's not FA naught anymore. This is going to be the molar exit flow from the first one. And this is FA is our final amount coming out. So, and what we can say here is FA1 minus FA, So what we could do is rewrite the, so, okay, let's call this FA2. And we can say here, FA1, we know equals FA0 times 1 minus XA. And FA2, we know we can write FA2 as FA1 times 1 minus XA2. Right, I should have said XA1 over here, right? So when we write this, then we are saying that XA2 is specifically the conversion only in the second tank, and that's 0.25. And okay, so let's call this XA2 dashed. So it's not the overall conversion X2, which is 0.5. This is the conversion 0.25. So we can write it like this, and then you would naturally go ahead and substitute this here, like so. So you could do that, but I would say much more conveniently, we'd rather write this as FA2 equals FA0 minus X minus XA2, the overall conversion of A. So you need to be quite careful of this, especially when you have multiple reactors in series. You want to be quite specific about that meaning of conversion. So you don't want to, these are two different conversions. This is a conversion in the second tank only. This is the overall conversion. And I'd rather work with this quantity, the overall conversion, right? So if that's what I mean by this X2, then let's see, then we have to be more careful here. So rate of change, so if I come back to this equation, right, so this is the equation that I'm trying to solve to get V2. So then I can write this here, oops, this here, FA2, and then your FA1 is this. And you can see you can group with FA0 here. And so you can add these two together. So you can say FA0 into, and the 1 minus 1 can cancel, and it's going to become a plus XA2 here. So this is XA2 like that. And that's all then in one term. And so you see, when you write it like this, when you work it out carefully, it then becomes clear that the right molar flow rate to use here is the original molar flow rate, right? When you do it intuitively, when you try to just guess your way through this, you would say, well, I'm talking about the second reactor, so clearly I should just write FA1 here. But according to what we showed here, that's wrong. And the reason it's wrong is that when we wrote X2 here, what we meant by that was the overall conversion. So if we are determining the overall, if we are choosing that to be the overall conversion, then it turns out we have to reference it with the total inlet amount. So, and that is a better way to do it, to keep the same reference. Whenever you deal with conversion, you are always converting with respect to some reference point, with respect to some inlet or some initial amount. So, so be quite careful with this, right? So that's how you can calculate the volume of the second one. Any questions or comments on that? Okay, again, I'm in the silent room. I don't know if I'm talking to myself. So you can work out, so you can just stick the numbers in, and you'll get a volume. I don't know, maybe it's, let's say 34 or something like that. So it's still not as good as the PFR. And you can see that graphically here. You can see you'll still get this extra piece here. So your 2 CSTRs are still bigger, but it's better than the 1 CSTR, okay? And of course, as you use more and more little volumes, then you get closer and closer to plug-like behavior. And so your volume gets better. But it's a more expensive thing if you were to make so many thousands of little reactors. Okay, so that's part B. And then we are told if we are using 2 CSTRs in series, what's the optimal conversion in the first reactor? So that's the one where let's do this as a new piece. So I'm just going to take this. So we said to answer that kind of question, what we do is we look for, I'm just going to draw this first. What we do is we choose a set of points. So it's not as convenient as the first 2 cases where you just go ahead and you can immediately draw something and find an area under it. For this case, using the optimal conversion, we have to search for it. And the way this works, I'm just going to draw another little construction here. So in this case, we know that this is where we are trying to go. And what we try to do in this case is maximize the rectangle that sits, that would be where our 2 reactors separate. So if we were to draw this like this, then we would say that for some x here, for some chosen x value, there exists a box which is maximized according to our choice here. So again, if we draw a construction line here, and then let's not take so much time on this. Right, so let's say we've got this construction line here. So we've chosen arbitrarily this point X. We don't know this is the best point, right? And in fact, to take a step back here, you see in the previous one, it just said assume equal conversion amounts, 0.25 and 0.25 in each one. So that's what part B was about. Now we are saying we don't know that that choice of 0.25 was the best. It could have been that if we choose a different conversion, we will overall get a lower volume, right? So as it is, we know that we will get that if we choose this as our intermediate volume, so if we choose 0.25, then we'll get a certain volume in each case. And we can try a couple of different intermediate conversions and compare the volumes. So you can try that. Just choose different conversions, 0.1, 0.2, 0.3, 0.4. Try each of those and see how your total conversion is changing. But what we also showed in the theoretical development is that you can determine the best position by simply taking the tangent at the point of interest. Not drawn too well. Line is fairly straight, so it is going to sit on there. So you choose a point. So do it first. First, just work out the volumes in each case. Then, using the method that we derived, you've chosen a point. Now you can estimate a gradient here. So if you read this, it's maybe that's 0.13, maybe this is 0.11. So 0.13 minus 0.11 divided by 0.28 and 0.15, that's the gradient there. And then according to what we derived, when that gradient is equal to that value, right, the value of that point divided by the value on the x-axis. So that ratio, when that ratio equals that gradient, then you are at your optimal point. So work out the gradient each time, see how close it is to that value, and you should find that the point where your volume is the lowest, let's say it turned out to be here, your overall volume was the lowest when you use that intermediate conversion, let's say it was that. If it, then at that point, you should find that your tangent gradient and your ratio are the closest to each other, right? So that's how you do part C. We are out of time. If you can spare 5 minutes, let's just talk about D. So in part D, we have three reactors in series. So 3 vessels used as reactors. Volumes are given. So in this case, we are given the volume. And here we want to find the sequence that gives the greatest overall conversion. So this is interesting. It's not clear to us whether we are going to put the 5 first or the 10 first or the 15 first. So of course, in this case, it is a monotonic curve. And what we can do is, so just note, in this case, we don't know what the conversion is, right? So conversion is not given. And so we want to get the greatest overall conversion. So because this curve is monotonic, do it both ways. Do it first 5, 10, 15, then do 15, 10, 5. And let's see if we can anticipate what will give us the best. Maybe think about the batch and the PFR, right? Which one do you think, what's better to have? Bigger volume first or smaller volume first? So, we do class evaluations. I wish it was a two-way thing where I also evaluate the class back and I say, hey, they were so quiet. I was just talking to myself the whole time. But if you think about it, you want to maximize the volume where the concentration is highest. So initially, where your conversion is low, you would rather use a bigger volume. You will get a higher reaction rate in the bigger volume. So I would rather have big volumes first, right? That's just what I think. You can try the numbers out and see if it works out that way. Okay, any questions or comments there? All right, if not, then I guess that's it for today. See you in the next one.